for you.
Oh, sorry about that, Riley. You said you had a question.
Yeah, that's okay. It can be related. It can be on record. The multiple integration homework says it's due Monday.
Uh-huh.
Is that still a thing?
We'll see where we are at the end of today.
Sounds good.
So that answer is TBD. How about we'll say that?
All right, sounds good.
Okay. But speaking of homework, questions about any of the homework sets? How's that stuff going?
Yes, are we going to be learning about 5 point, was it the non-rectangular ones?
Okay, I don't, first of all, Jordan, I don't know what section numbers are what, so I can't answer it to that. And if you're saying non-rectangular, I'm guessing you mean polar? Are you talking about polar coordinates?
Double integrals over general regions.
Oh, yeah, no, we'll talk about that today. All right, so Victor just threw in that it's long, but it's okay. Is that what most people are thinking? All right, well, seeing nobody's like really yelling at me to do any of them, let's dive in. Let's dive back into working on these double integrals so we can start getting a better feel for them, how they work, how we set them up for various regions, and what they're good for, right? We'll start talking about some of the things I already kind of hinted at, volumes, but that's a very small portion of what we use double integrals for. So give me 1 second here and I'll go hop to the whiteboard. All right, so let's talk double integrals. We're kind of, we started getting the idea of how these things work and what they do last time, but let's go into a little bit more detail. Let's actually spend some time playing around with them, looking at, integration man vertically versus sideways, and just some of the things that we can do with them. So first of all, hold on a second, let me adjust my screen here just a touch. There we go. All right, so let's go back to the idea of the double integral. So basically, when we're doing a double integral, it's just an integral followed by another integral. So we literally write them back to back. We're going to have whatever our function is that we're integrating. And then we have to make sure we specify what our variables are, and they can be any order, whatever we want. So let's do a, say, dx dy here. And do you guys remember which one do we do first? Like in this case, are we going to do x first or y first?
X.
Yeah, we're going to do x first because we always just take them in order. So that means that the bounds on the inner integral can actually be functions of the other variable. So I'm going to call them g1 and g2 of y. And then the outer bounds are constant constants. Okay, so this is the setup. And we do the integration as partial integrals, right? So integrals where we treat all the other variables as constant. Okay, so there's a setup. Let's actually do one just to kind of refresh our memory on how these things work. So let's say we're going to integrate from 1 to 2, and we're going to integrate from x to x cubed. And let's say that the function that we're integrating is xy squared. Now, I intentionally did not put on the differentials because I want you to tell me which way we're going. Is this going to be dx dy or dy dx?
dy dx.
Okay, so you say dy dx, Bradley. I can tell there's a little bit of a question mark in your voice.
Yes.
Why do you think dy dx?
Because if we integrate with respect to y, we're then going to plug in x values after, and like as our bounds. Therefore, it's the only way we're going to be able to do it.
That's exactly it. It's these guys right here. The fact that you see x's in these bounds, in the innermost bounds, tells you that the other letter is the one that we're integrating with respect to. Okay, so we can always tell, we can always know exactly what it's going to be. So this does need to be dy dx. All right, so when we integrate this, xy squared, the x is constant, so it just stays like that. The y squared becomes y cubed over 3. And we're going to evaluate these at x and x cubed. So we put x and x cubed in for the y. And now we're integrating from 1 to 2. X to the 10th over 3 minus x to the 4th over 3. And now this is just a good old single variable integral. We know exactly what to do. So that's going to give us x to the 11th over 33 minus x to the 5th over 15 that we evaluate at 1 and 2. And I'm just going to put a question mark there because I don't really care what that number is, and you know what to do now. You're going to plug in your 2, you're going to plug in your 1, and then subtract those values using the fundamental there. Okay, so this is the process. It's just integrate, but they're partial integrals that they're iterated. They're done in order. All right, so hopefully that's a good kind of warm up on how these things work. But let's talk a little bit more about the regions over which we're integrating and the like, and practice some more with switching the bounds and setting these things up. But before I move on, are we okay with this? Thumbs up? Any questions? All right, I'm seeing some thumbs up and no questions, so I think we're probably good. All right, so in general, when we've got one of these things, the bounds specify the region. And so we're going to call this the region of integration. When we had single variable integrals, we integrated over an interval of numbers, right, from A to B. But now these things form the region of integration. So basically the question is, how do we get R from the bounds? And we'll look at the two different cases. We'll look at when we've got dx dy versus when we've got dy dx, what the difference is. But let's start with this one. If I was going to draw this region, here's how I do it. I start by looking at these two functions, g1 and g2. Now, since these are functions of y, that means they're going to be turned sideways. So we're going to have some kind of a function that's sideways. So this would be our g2, and this is our g1. So before I move on, are you guys okay with me saying that these are sideways functions? Right? They don't pass the vertical line test. They're definitely not functions like you think of, because these aren't functions of x. They're functions of y. So these are g1 and g2. And then we also look at a and b. Now in this setup, a and b are y values. So y equals are horizontal lines. So also somewhere on here are a and b. So we can draw those out horizontally, pretend that that's a horizontal line. And so the region over which we're integrating is this guy in here. I'm going to put a big R, stands for region. But it's this piece right here. So if you ever want to specify the left and right-hand sides of this region with functions, we're going to start with dx. All right, so the functions you notice are on the left and right, and that's why we have dx. Now, if we were to turn this around, so we've got the integral a to b, but now g1 of x, g2 of x, this is going to be a dy dx. Again, what it tells us is the fact that these are functions of x, since our x is here, it needs to be a dy dx. And for this one, the picture has functions like you're used to, oriented the way that you want them to be. Okay, so here would be our g1, and here's our g2, or sorry, the other way around is g2 of x, g1 of x. Again, there are some values a and b, and those give us the vertical ends of this region. And so now in this case, R is here. So notice the difference. This first one, the functions, the kind of varying sides, are on left and right. For the second one, the functions, the varying sides, are on top and bottom. So if you're ever presented with a region that looks like one of these two, you want to use one form or the other if possible. Okay, just because it's going to be easier. Now, obviously, we could have it such that all four sides are wavy or functions or something like that, and then we have to approach it differently. But in general, this is what's going on with those regions. Now, I introduced you to Integration Man last time, right? My mathematical superhero. And I use Integration Man to help me visualize this, because Integration Man is always oriented. He's always, his body, you know, head to foot, is always oriented in the direction of the first variable when we're integrating. So like in this case, since it's a dx, remember x is left and right. So Integration Man is in here in this region, left to right. His head is always resting on the top function, and his feet are resting on the bottom function. And then he walks from bound to bound. So he goes from A to B. And you think about it, he stretches, his height changes, his feet are always on this bottom function, head is always on the top function. And so as he's walking and stretching, he's filling this entire region. So he's mapping out the region. Think about with the second case here, dy, that tells us Integration Man is in the y direction. Y is up and down. And again, his head is on the top of those functions, and then his feet are on the bottom function. And again, he's going to march from A to B. And as he does that, as his height changes, he fills up that entire region. So I'll talk about Integration Man. I'll just mention him, or I'll say, okay, hey, we're going to set up this region. Which way do we want Integration Man oriented? It's just a visual way for us to figure out which is going to be easier in terms of setting up the integrals. All right, now it turns out it doesn't matter which way you do it. You can have Integration Man be oriented sideways or vertically. As long as you set it up properly, you will get the same value. But I did show you last time an example where one orientation was actually integrable, but the other wasn't. Right, there was the one that gave us like an e to the x squared. But if we oriented in the x direction, we were screwed. But in the y direction, it ended up giving us something that we could then integrate. So sometimes you are forced one direction or the other, but other times you're not. So let me give you an example of an integral. And what we'll do is we'll set it up both ways. We'll set it up as a dy dx and as a dx dy. And we'll think about which one's easier, which one do we want to use, but we'll run them both so we can see that we get the same value.
I have a quick question for you.
Sure.
So you said we can't integrate e to the x squared?
With
Is it
respect
that-
to x, correct.
With respect to x, yeah. Is it the fact that we literally can't do it, or we as a class don't have the tools to do it?
It's not just you guys as a class.
Okay.
It's impossible.
Okay.
It's an impossible thing. Not even Larry can do it. So think about that. For those of you who don't know Larry, he's the other calculus teacher at our college. So, but no, nobody can. It's impossible. You can actually prove that it's not possible to integrate it. All right, so here's what I'm going to do. I'm going to give you the region and the function that we're integrating, and then we're going to pick the two. We're going to set up both directions and then calculate them, see that we get the same thing. Okay, so here's what we're going to do. First of all, the region that we're going to be integrating over is this one. It's a triangle. And these vertices are 0, 0, 1, 1, and 2, 0. Okay, so this is the region that I want to integrate over. And the function that I want to integrate is just a really easy function. F of xy equals x. That's all I want. So I want to integrate this guy over the region. All right, so we all clear with what we want to do? All right, well, let's try to set up integration man. Use integration man to set up the integrals. And we'll do it again, both directions. We'll have one of them be a dx dy, the other will be a dy dx. Okay, so let's start with dx dy. So we're going to have a double integral. We'll fill in the bounds as we go, but what we're integrating is the function x. And let's go dx dy. So which way is integration man oriented? Is he standing upright or is he on his side?
Upright.
All right. So we good with that? He's upright? All right. You should not be good with that he's upright. So thanks for everybody going side and no. Okay, so remember how we decide. It's the first variable, right? It's a dx, so he's going in the x direction. X direction is on his side, so he's going to be oriented this way. So if we're going to do a dx dy, he's going to be oriented on his side. Right? So there's one picture of integration man. There's another one a little bit later on. He gets really short when he gets up in here. Right? But that's how integration man's always going to be oriented. He's going to be on his side because of the x. All right, so he's on his side, which then means we need to figure out the functions that determine where his head and his feet are. Now, for this region, they're lines, right? This is a line, that's a line, so these will be pretty easy for us. All right, so Victor, yeah, you gave me one of them, y equals x or x equals y. Which one is that, his head or his feet?
Feet.
That's his feet. Yep. Okay, so this one right here, this is good old y equals x. And so for the bound on the bottom here, I'm going to put y. I'm not putting x, I'm putting y. Why? Why y and not x?
Because you're supposed to, but I'm a little confused because we don't have a y.
Okay. And it's because, remember this first one, I'm integrating with respect to x, which means these have to be constants with respect to x. So that means no x's, but I can have any other letter in there I want. So this, I'm going to go from x equals y. This is the hardest part for sure, is wrapping your head around what goes where. Just remember, it all comes down to this first differential. Not only did the first differential tell us which way integration man went, but it also tells us what letters are allowed in here. We're not allowed x's, which means for a two variable thing, they're going to be y's. So we want to think of those as x equals something. So this is x equals y. All right, well, let's get the other line. So the other line, you may notice, has a slope of -1. If we extended this out, it would have a y-intercept at 2. So this is y equals -x plus 2. That's that. All right. So then what's going to go as my upper bound? What am I going to put up here as the top bound for this first integral? So Victor just typed in y minus 2. I love the fact that those are y's. But yeah, there you go. Switch it around. Minus y plus 2. We need to solve this for x. If you were to solve this for x, it's equal to -y plus 2 or 2 minus y. And so that's what's going to go up here as my upper bound. So they have letters in them because they have to, right? Because these are not constants. But the letters that are in there are y's, not x's, because they need to be opposite what this is. All right, so there are the bounds for integration man in terms of his head and his feet. So then we need to put on the bounds for this outside integral, which are going to be constants that tell us where he's walking, how far he's going. And these are y values. So what's the smallest y we see?
0.
Well, Victor just jumped the gun here, but yeah, but so Bradley, the smallest y is 0. And we're going to keep walking until we reach up here, which is y equals 1. So the bounds on this are going to be 0 and 1. So there's the integral. If we have integration man on his side. So if we go with a dx dy, this is what this integral looks like. But now that it's set up, it's, well, business as usual. We're going to integrate x. We're going to get x squared over 2. We'll plug in these bounds, subtract it. Now it's a function of y. Integrate that thing. Plug in the bounds of 1 and 0. Subtract it. And that's going to give us our value, the value of this double integral.
So we don't necessarily need another y attached to that. Like we don't need an x times y at the beginning.
Oh, in here?
Right? Yes.
No, this function can be anything. It could be only y's, it could be only x's, it could be some combination of x's and y's, it could be a constant. The function that we're integrating is kind of irrelevant in terms of setting up the rest of the integral. It will definitely change the value of the integral. But yeah, there doesn't necessarily have to be a y in here. Any other questions about this one? All right, well, let's turn it around. Let's do it as a dy dx, right? Because integration man can go the other way just as well. So what about if we instead did a double integral of x, but this time let's do dy dx. So let me erase integration man here because he's no longer on his side. Now integration man is going to be vertical because our first variable is y. So integration man is going to go in a y direction. He's going to be up and down. So that means he's going to be teeny tiny integration man there, taller integration man here, taller there, getting shorter back again, right, until he gets a little tiny. But there are a whole bunch of pictures of integration man as he's walking. Okay, but now he's vertical. So we want to do the same thing. We want to think about where is his feet, right? Where are his feet? What function determines his feet? And then what function determines where his head is? So let's start with his feet. Where are his feet always?
X equals 0.
Okay, except not x equals 0, it's y equals 0. But these are y bounds, so I do want a 0 here. Right? Y equals 0. So sometimes those bounds don't have letters in them. And that's when those sides of the region are constant. So either horizontal lines in this case, or vertical lines if we're in the dx first case. Okay, so his feet are at y equals 0 as he's marching along, right? What about his head? All right, so Victor just says y equals 1. Is his head on the function y equals 1?
Not really.
What does y equal 1 look like?
It's just a horizontal line.
Yeah, it would just be a horizontal line here. And his head isn't always bumping up against y equal 1. Right? His head's bumping up against this side right here for a while. Then it switches and his head is on this other function. All right, so here's what's kind of crazy. If you look at this first bit, his head is on y equals x. So I'm going to put here y equals x. But the problem is his head switches to a different function. after a while, right, his head is bumping up against y equal x, but then after a while it starts bumping up against y equals negative x plus 2. So that means we actually have to split this into 2. So if we got him oriented this way, unfortunately, we're going to have to do 2 integrals, because the function that determines where his head is switches. All right, so Victor just said, I already prefer dx dy for this one. And I agree. This is one where dx dy is definitely the way we want to do it, because it's only going to take 1 integral instead of 2 integrals. And what we're integrating isn't a problem. We can integrate it both ways. So there are definitely going to be times we want integration man sideways. Your instinct is going to have him be vertical. That just feels better because we're used to functions of x. But vertical integration man is not always that great. Well, let's go ahead and finish this though. I don't want to leave it here. Let's think about, as integration man walks, which x values are such that his head is bumping up against y equal x. Well, it's going to start at 0. He's walking, 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 and then he switches at x equal 1. So there's going to be integral from 0 to 1 for the first piece. Then once he reaches x equals 1, now his head is on the other function. So that's going to be the start of the second integral. It's going to start at 1, and it's going to continue until x equals 2. So sideways integration man gives us this integral. Vertical integration man gives us this pair of integrals that we have to add. So just watch out for that. Sometimes it's a little bit better to go sideways than vertical. And vice versa. Like, it totally depends on the region. And that's the other thing that I really want to stress here and reinforce, is that which one you want to use is primarily determined by the region. Use the region to help you figure out which way is better to set up the integration. All right, now we did something here that we should probably talk about whether it's legitimate or not. And that is the fact that I basically split this into 2. Right? When I set it up vertically with integration man standing upright, I basically divided it into 2 chunks. And I'm going under the assumption that if I do the integral over one chunk and then add it to the integral over the other chunk, that I'll still get the same value. So what do you guys think about that? Is that reasonable? Does it seem like it makes sense? Is it okay? What do you guys think?
It seems reasonable, but I suppose we could do it to find out.
Yeah, maybe we should, just to confirm. Okay, so Victor just put in the chat room, yes, but it should be continuous. By continuous, I'm going to guess you mean the region, or do you mean the function? The function? All right, well, it turns out that the function itself, and I don't know if you mean the function that we're integrating or the function that forms the bounds. The bounds, okay, because the function that we're integrating has nothing to do with this at all. If these bounds are not continuous, it's hard to actually even specify it as a region. So usually it's closed. Usually we don't have this problem. But here's basically the analogy. Anytime we do something with multivariable integrals, I like to go back to one variable integrals. I like to look at those and think about what did we have similar that applied there. Well, do you remember when you had something like this? Where maybe you had a region, a function like this, and we wanted to find the area under that curve, and you went, oh, here's what we'll do. We'll split it into 3 pieces. There's going to be this one, and that one. So you could do, this is a triangle, this is a rectangle, it's supposed to be a circle, but a quarter circle. Kind of remember doing that?
Yeah.
And what we could do, like if we said that this was A, B, and C, instead of having the integral from 0 to C, we wrote it as the integral from 0 to A plus the integral from A to B plus the integral of B to C. So we did that when it was single variable, and kind of the whole idea behind that and what allowed us to do that was that we were breaking up this interval, but we were breaking it up in such a way, it was called a partition. Don't know if you remember that name, but it was a partition of that interval such that everything in that interval was accounted for, and there was no overlap of the regions of the intervals. And we saw that this was totally legit. Well, we can extend that now to second order. Right? If we're going to do a double integral, as long as the region over which we're integrating gets partitioned so that everything in that region is still there, and there's not been any overlap, we'll get exactly the same integral. All right, does that make sense?
Yeah, sounds good.
So what's beautiful, like really what's beautiful is that everything we did with one variable, we can just extend it up to the next dimension. So instead of talking about intervals, now we're going to talk about regions. But if we can split apart intervals, we can split apart regions. And why this is especially nice, this is especially nice because we can end up having regions like this one, and we can make our life oh so much easier if we do this the right way. All right, so here's what this region is going to look like. We're going to have a parabola up here, and then a triangle here. We'll go horizontally, and then let's just do this. Okay, so I'll even tell you what all these different things are. The one that's parabolic, the equation of this is x equals y squared minus 1. So that's this guy. This one's a line, and it's just y equals negative x minus 1. So then you know that this is actually y equals minus 1, since that was the intercept of this thing. And let's just say that this one is x equals 2. So this is my region. Now what I want to do is just set up an integral, or integrals, however we want to do it, so that we're integrating a function. I'm not going to give you a specific function. We'll just call it f of xy. But let's think about trying to split this up in a nice way for integration. Now, as it is, if we just tried to do it in one, it's going to be a little tricky. Like think about integration man vertically. If integration man is set up vertically, so over here on the left, there's a little integration man. Here's a bigger integration man. Another integration man, right? So here's vertical integration man. And notice that it does end up creating two different integrals because his feet change. His head's always in the same place, but his feet change. So then you might go, okay, well, what if we turn him sideways? I'm going to actually overlap just so you can kind of see, but if we did it sideways, I'll make it black here. There's integration man, here's taller integration man, and then integration man starts getting shorter again, and so on, right? And so notice here, his head is always on the same side, but his feet, again, swap. So either way, we're kind of toast. We're going to have to do at least two integrals. But we could even do this in such a way that we have lots of constants for our bounds. So let me erase integration man, and let me show you how I would probably try to break this up. In general, you're going to like vertical and horizontal sides, because when you put those in as bounds, they're just numbers. So I try to do everything I can with just horizontal or vertical sides. So I would actually split this into 3. And here's how I would split it. I would split it into, this is one of my regions. There's a second region, and then my third one. Okay, so I'm going to call them 1, 2, and 3. And let's set up an integral for each one of those 3. Okay, so here's for number 1. We're integrating whatever our function is. Don't really care. And I'm actually going to do this one sideways. So I'm going to do him dx dy. So in that region, if he's sideways, his head is always up here at x equals 2, and his feet are always on this parabola. Now, I did this sideways because I've already got this as x equals. So his feet are y squared minus 1, and his head is at x equals 2. Everywhere in region number 1, that's going to be the case. His head is always bumping up against this vertical line, and his feet are always on the parabola. And then I need to know how far he's going in the vertical direction. Well, he's starting at y equals 0. And the question then is, how far does he come up? How are we going to be able to figure out what that y is?
Plug in 2 for x, solve for y.
There you go. Yeah, we know this is at x equal 2. It's an intersection point. So we get 2 equals y squared minus 1, or y equals the square root of 3. So there's the bounds for region number 1. So now we're going to add to that. Let's do region number 2. Now, region number 2, again, this one's actually pretty nice because either having integration man horizontally or vertically will work. I'm going to go ahead and do them vertically. So I'm going to do a dy dx. So integration man in here is going to look like this. Let's start with his head. Where's his head?
Y equals 0.
At y equals 0. Cool. So that's going to be a 0 up there. And then his feet or this line, which is already solved as y equals, so minus x minus 1. So then the last question is, what are the x values over which he's marching? Well, he ends at x equals 0. So that'll be the top one. And where does he start? What's the y over there?
-1.
Or sorry, the x.
-1.
It's going to be -1. Y is 0. So if we let y equal 0 and solve for x, we get x equals -1. Okay, so there's the second one.
How do you determine which way he starts, though, integration man?
Always left to right. Or always down and up. So always from smallest to biggest.
Okay.
Right? You think about when you do a regular integral and you integrate from a to b, you're going from left to right. So that's going to be the same here when he's marching horizontally. It's from left to right. And then vertically, it's from down to up, because down is smaller numbers. We go from smaller to bigger. That's a good question. All right, so there are the bounds for region number 2. Now, region number 3 is like the best region ever because it's a rectangle. And rectangles, they're really nice because all of the bounds are constants. So let's go ahead and set them up vertically, just for the sake of something. Let's do dy dx. So if integration man is vertical down here, his feet are always on y equals -1, and his head is always on 0. And if we think about him marching from left to right, what are the bounds on x?
0 to 2.
0 to 2. So there's the bounds for region number 3. So we split it into 3 integrals, which, as long as f isn't that complicated, integrating it a few times isn't that big of a deal. But we've made it so that most of the bounds here are numbered. But let me show you why rectangles are really awesome. Like, we set it up this way so that integration man was vertical. What if he was sideways? Let's think about what he would look like if he was on his side. So this is going to be a big or, because let's do it dx dy. So where are his feet always in this rectangle in region 3?
X equals 0.
X equals 0, and the head is always at 2. That'll be 0 to 2. And then over which y's is he progressing from lowest to biggest?
Negative
So from
1 to
negative
0.
1 up to 0. So check these two out. Notice what happened when we swap the bounds, or swap the order. We literally just interchanged the two integrals. Rectangles are awesome. Rectangles are beautiful. You're going to love them because you can't really go wrong setting them up vertically or horizontally. Either way, you should be good.
I'm sure I could find a way.
I know those are pretty brave words of mine, huh? Oh, you can't mess those up, you guys. Uh-huh. Oh, yeah? Hold my beer. Right? This is definitely a hold my beer moment. Anyway. Okay, so let me just tell you a little more theory behind this, like what's going on. So this whole breaking it up into regions, totally legit, everything's fine. Similarly, we can use the other kind of rules of integrals, like If I've got two functions I'm adding, I can split it into two and add them separately. If I've got constant multiples, the constant multiples go for a ride and blah, 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 blah. Like all that stuff happens. But one other thing that we're sort of taking for granted is this whole, I can swap the bounds and it works, right? Like when I put here this big OR, my contention is that this blue integral and this black integral will actually give me the same value. And so that it's fine to do that. It seems right. Yeah, I mean, it feels like it should happen. But we also know that a lot of time in math, when we have that sort of situation, we end up getting, that's when it comes back to bite you in the ass, right? Where you're like,
Like
oh,
a change of signs or something.
Yeah, exactly. Or some sort of weird, there's always something that makes you maybe go, well, shit, maybe something's wrong. But it actually was proven by an Italian mathematician by the name of Fubini. It's kind of a fun name. So there is Fubini's theorem, which we're not going to prove, but Fubini basically broke it down into, you may remember when I first started kind of introducing you to the double integral, I said how it was sort of like we're finding volumes under surfaces. And so you're breaking it into a bunch of little rectangles of dx's and dy's. And you add up, it's a double sum. Well, he basically did let's slug it out as doing the sum of x, then the sum of y, and then reversed it and saw that it must be that way. So it is actually okay. Somebody did prove it, so it is totally fine for us to swap bounds, swap directions. We can put integration man whichever way we find most convenient for the specific region and or integral. Okay, so this is something you should definitely practice. Definitely practice this, because you run into situations where you can't do it one way, but you can the other. Or you'll run into situations where in one way you got to do 3 integrals and the other way you only have to do 1. Okay, well, be a good little mathematician and be lazy. Do it just the one way, even if all it requires you to do is turn your head to the side. Right? I mean, you turn your head to the side and now x's and y's look like y's and x's. No big deal. Be willing to do that, because sometimes it will save you a lot of time. All right, so we're pretty much out of time, so I'm going to stop here. Just a reminder that the next set of homework is due on Monday. I think I'm going to go ahead and give you guys an extension on the set from the double integral, the most recent one. I don't remember what number that is. It's 5 point something.
5.1 and 5.2, I think.
I'm going to definitely have you do the first of the double integrals. I think maybe the second one I'm going to extend. So I think it's just the last one of this set. So I'll be sure to post a note. You'll also see it change, not this afternoon, but probably tomorrow. But I will definitely change that. Other than that, keep working on this, and I will see everybody on Monday. All right, so have an awesome weekend.